Hello, this is Adam Paulson welcoming you to this Bite-Sized Bio webinar. Today's presentation is titled Confirmation Bias in the Scientific Method 1, How to Avoid Confirmation Bias, and is being presented by Danny Spencer Adams from Tufts University. Danny Spencer Adams is the President and Chief Science Officer of Lucell Diagnostics, a medtech company that develops novel diagnostics for cancer and other diseases. With over 15 years of experience as an experimental biologist, she is passionate about applying her expertise in cell biology, microscopy, and bioelectricity to create innovative solutions that improve human health and well-being. As always, we'll have a question and answer session after the presentation. For today's session, Danny will be joined by Amanda Welsh during the Q&A. So please type any questions that you have into the questions box, which appears on the top right panel of your screen, and Amanda will put them to Danny for discussion. Details of how to access the on-demand recording of this webinar will be sent to you by email shortly. So now over to you, Danny, for the presentation.
Good morning or good afternoon, depending on where you are. Thank you for inviting me. Welcome to my office. I'm going to be talking over the next two webinars about the scientific method. Now that's, of course, a huge topic. I could never actually cover everything in 2 hours. So what I've done is I've kind of cherry-picked things that I think are the most useful and practical things to keep in mind as you go about doing your science. And when I started to think about what is it about the scientific method that makes it special or distinguishes it from pseudoscience, for example, it's that it really is designed, it has built-in traditions and conventions, all of which help us suppress our natural tendency to look for confirmation for what we already believe. So that's how my title became How to Stop Thinking Like a Human, the Scientific Method as a Cure for Confirmation Bias. So I love this cartoon. So part one, I want to talk about confirmation bias and why we all read newspapers that pretty much confirm what we already believe. Or we go to links that convince us that we are right. Well, as I said in the title, the current term for this is confirmation bias. But of course, it's been recognized for a very long time. Humans always look at themselves and always try to be philosophical. Here is an example from 1970 from Paul Simon's song, "The Boxer, a man hears what he wants to hear and disregards the rest." A little earlier than that, we have Harper Lee talking about this. People generally see what they look for and hear what they listen for. That's from To Kill a Mockingbird. Good old George Bernard Shaw, the moment we want to believe something, we suddenly see all the arguments for it and become blind to the arguments against it. Okay, another couple of 100 years earlier, we have Francis Bacon. With a slightly more flowery language, it is the peculiar and perpetual error of the human understanding to be more moved and excited by affirmatives than by negatives. Francis Bacon will come back a little later. Going way, way, way back to Plato, from an article by Nick Romeo, he points out that Plato, in his dialogues, depicts people believing what they want or what they are predisposed to believe. And he specifically says that that's Plato's version of confirmation bias. And finally, as far back as I could find, this very poetic version of confirmation bias from Lao Tzu: the ever-wanting soul sees only what it wants. So this is not a new thing. Humans don't change that much, even over millennia. So part two, the question is, well, why? Why do we do that? Why do we seek out confirmation rather than information, or even worse, refutation? And just as a side note, don't be embarrassed that you do this. Everybody does this. I highly recommend checking out explorable.com/confirmation bias. It's a charming video of confirmation bias in action. So check that out when I'm done. But we all do this. It's a completely human thing to do. And just as an example, I didn't spend any time looking for evidence that confirmation bias doesn't exist. So this is a completely human thing. And it may be of some consolation if you are aware of when you do it. Michael Shermer, who is a wonderful thinker, says that if you're intelligent and well-educated and very good at pulling facts, you're going to be even better. So confirmation bias, the better you are at it, the more intelligent it means you are. Okay, so back to the main theme. Why do we do this? Well, there are quite a few hypotheses and relevant observations out there. I'm going to present just a couple. One of my favorite cartoons, this actually was first drawn many, many years ago, but it does seem to apply in all time zones. Looking at arguments that might prove you wrong is painful. It's a really hard thing to do. And I'm going to call it that, I'm going to just dub that the extreme discomfort observation. And this is from philosopher Frantz Fanon. Sometimes people hold a core belief, and when presented with evidence that works against that belief, the new evidence cannot be accepted. It is extremely uncomfortable. They will rationalize, ignore, and even deny anything that doesn't fit in with the core belief. Just this past February, the New Yorker had a short article by Elizabeth Kolbert about where confirmation bias comes from. And one of the hypotheses she talks about, I've called the social hypothesis. And she describes this thus: sociability is the key to how the human mind functions, or perhaps more pertinently, malfunctions. Habits of mind that seem weird or goofy or just plain dumb from an intellectualist point of view prove shrewd when seen from a social interactionist perspective. And the example given is our ancestors were primarily concerned with making sure that they weren't the ones risking their lives on the hunt while others loafed around. There was little advantage in reasoning clearly, while much was to be gained from winning arguments. She also talks about what I've dubbed the physiological observation, and this is that people experience genuine pleasure. There's a rush of dopamine when they're processing information that supports their beliefs. So it hurts to be disagreed with, and it's pleasurable to have your ideas confirmed. I expect everybody has experienced that. I'm also going to add the danger hypothesis, okay? So when something dangerous goes by, it may be very important to think quickly rather than to stop and take in all the information. So there are very important moments as far as selection when acting quickly is more important than careful thought. So for example, getting away when you see a shark is a good idea. It may turn out that it was harmless, like the nurse shark that just went by. But that's not so important when you're making the decision.
I'm hoping that
so our ancestors who did not get eaten by sharks are the ones that stayed alive long enough to become our ancestors. So we inherited those hair triggers.
Okay, I'll talk to you later.
Now, to make those instantaneous decisions, we have to rely on what we already believe. There simply is no time to collect more information, because if you do, your brain might get eaten. So you don't want to think, you simply want to get away. The term for that idea of what we already believe is heuristics. And our heuristics, which you can think of as mental shortcuts, are what allow us to make decisions quickly, and that's good. The problem is they can also make us lazy about gathering evidence, even when there is time, and even when it's evidence and not escape that matters. And of course, doing science is an activity where evidence matters. So these hair triggers are going to be a problem. So the question is now, how do we overcome these very human tendencies and do good science? And that brings me to my title, How to Stop Thinking Like a Human. Well, of course, like with anything, recognizing the problem is the first step. And I'm going to just say it. The antidote to confirmation bias is the scientific method. Now, I Googled scientific method to try to find good quotes or good images, and there were 13,900,000 results. So I decided that I really couldn't filter through those to find things that are particularly illustrative. And in addition, like the term confirmation bias or the idea of it, ideas and quotes about the scientific method go back at least to Plato. So instead, I'm going to use as my text a 1964 paper by J.R. Platt. And this paper is called Strong Inference. You can see it's not particularly flashy first page here. So strong inference, certain systematic methods of scientific thinking may produce much more rapid progress than others. So Platt is actually going to talk about the scientific method in the context of saying that it's not even just that it makes for better science, it makes for more rapid science. Science will actually progress more quickly if these techniques, this way of thinking, is used systematically and regularly. So he observes that in certain laboratories, and in fact in certain whole fields, and he talks about theoretical physics and molecular biology, which was quite young at the time he wrote this paper, and he observes that in those fields where scientific thinking is the rule and is practiced carefully and thoughtfully, the science itself proceeds faster. And he puts it this way: rapidly moving fields are fields where a particular method of doing scientific research is systematically used and taught. An accumulative method of inductive inference that's so effective that I think it should be given the name of strong inference. So there is his title. As another side note, I want to give you a quick reminder of what inductive inference is. It's always compared with deductive reasoning. Deductive reasoning is you start with a theory, for example, an axiom or syllogism, and you follow it logically to new truths. So deductive reasoning is all mammals have lungs, dogs are mammals, therefore dogs have lungs. So the new information follows directly from the theory. Inductive reasoning is where you start with the evidence and you construct a best fit theory based on the evidence. So where deductive is theory first, evidence after, inductive reasoning is evidence first, theory after. So for example, every quokka we observe smiles, therefore quokkas smile, and I'm going to check that out. Okay, there they are, the quokkas smiling. Okay. And despite that very familiar line about brilliant deduction, one very famous practitioner of inductive and only occasionally deductive reasoning is, of course, Sherlock Holmes. And Arthur Conan Doyle puts into Holmes's mouth the following quote from Scandal in Bohemia. "It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts." So he's very clearly a proponent of inductive reasoning rather than deductive reasoning. There's all sorts of very funny conversations you can find online where people try to understand why, if Doyle felt that way, why did he have the character say brilliant deduction? Anyway, perhaps you have read this story in other guises. The brilliant detective or the amateur solves the mystery using inductive reasoning, while the plodding dumb policeman blows it. And that's because he uses deductive logic, and his confirmation bias makes him unable to see all the evidence. So in the case of Sherlock, that, of course, that role is played by Lestrade. Okay. Gets an idea in his head and he tries to prove it instead of looking at the evidence and then figuring out what's happened. Okay, so that's the end of my aside about deductive versus inductive reasoning. So back to strong inference. Strong inference is a means, the term, Platt's term, strong inference, means the systematic application of the method of inductive inference described not by Sherlock Holmes, but actually by Francis Bacon. So here's Francis Bacon back, offering more to scientists. Okay. And in the paper Strong Inference, Platt addresses confirmation bias by quoting T.C. Chamberlain, a geologist writing in the journal Geology. And he gives a charming description of confirmation bias, but importantly, he suggests a method for how to avoid it. Okay. There's Dr. Chamberlain. The moment one has offered an original explanation, at that moment, affection for the intellectual child springs into existence. And as the explanation grows, parental affections cluster about the offspring. There is then the imminent danger of an unconscious selection and of a magnifying of phenomena that fall into harmony with the theory and support it, and an unconscious neglect of phenomena that fail of coincidence. So he's saying that confirmation bias happens because we fall in love with our ideas. Right? His suggestion is, don't fall in love with your ideas. Multiple hypotheses distribute the effort and divide the affections. The investigator becomes parent to a family of hypotheses and is morally forbidden to fasten affections unduly on any single one. So you can avoid falling in love with your idea by starting out with multiple ideas. So in this sense, strong inference consists of applying the following steps to every problem in science: formally, explicitly, and regularly. Okay? And here I've tried to indicate that they're written in stone. Okay? 1, devise alternative hypotheses. Don't let your unconscious bias fall in love with one idea. 2, devise crucial experiments, each of which, as nearly as possible, excludes one or more of the hypotheses. So you're going to winnow out hypotheses by disproving them. Carry out the experiment so as to get a clean result. And finally, recycle the procedure. So go back now and devise new hypotheses based on the results. So to recycle the procedure, making sub-hypotheses or sequential hypotheses to refine the possibilities that remain, and so on. Okay, what does this look like in action? Well, you've probably experienced it in a chemistry lab course. Okay, it might have been called a qualitative analysis scheme, and it may have been presented to you not as a scheme, but as step-by-step instructions telling you exactly what to do. So on the top of the paper, it may have said something like, the TA has placed some unknown substances at your bench. Your job is to identify all of them. Follow the directions, and just like real science, it will work perfectly every time. Dumb pedagogy joke. Okay, so you have all these substances, and the question you're asking is, what is this stuff? Okay? And you have been given a list of all the things it might be. And this list of possibilities, those are your alternative hypotheses. And the first experiment you're going to do is you're going to put them into water. And some of them will go into solution. Some of them are soluble. Others are not so soluble. So the result of this experiment is going to be whether it's either going to be soluble or it's going to be less soluble, insoluble. So you do this experiment, and what you find is that you now have narrowed things down a little bit. So we're going to pretend that the substance was less soluble. And that's because less soluble is going to tell us that it's not any of these things. And there's way more of those things. So if we followed the soluble result, we'd be here forever. But let's say that the result of the experiment is that the substance you have is less soluble. Okay, so now the alternative hypotheses, we're going to recycle the process. The alternative hypotheses are that it's one of these four. The next experiment, okay, we're going to put it in acid. Okay, and the possible results of that are the same: less soluble, soluble, or it makes bubbles. Okay, so those are the results we may find. Okay. We're going to do it again. If those were the results, we have the following hypotheses. If it was bubbles, it was calcium carbonate. If it was less soluble, it was flour. Okay? If it's soluble, again, we don't have to worry about it being these other two things. We have disproved that it's these other substances. We've excluded them. And our alternative hypothesis now is it's either one of these two substances. Our final experiment is we're going to test them with litmus paper, and we're going to find that it's either neutral or it's basic. And if it's basic, that's going to exclude the calcium molecule, and if it's neutral, that will exclude the barium molecule. So what you've done is you have narrowed down the possibilities by excluding things that it cannot be given the result of the experiment. So if something is less soluble in water and in acid, it's flour. If it's less soluble in water but more soluble in acid, it's one of these two compounds. And that's the logic. And that's the idea of iterating this process of coming up with alternative hypotheses, doing the experiment, looking at the result, interpreting it, and that way working through to the answer to your question. Okay, so those are the steps. Platt actually suggests keeping that chart up on a wall so that everyone involved in doing all these experiments can write in the ideas and the suggestions and the results and the interpretations, all those things, so that communication is completely open among the whole group and nothing gets lost. And so I've put up here the chart that's to my left here. That's my chart of the process of a series of experiments that I'm currently doing. Mine's not quite so neat as the handout I just showed you, but you can see this process of, depending on the answer I get, that tells me what to try next. Okay. I want to zoom in now. So that was step one. That was alternative hypotheses. Step two, devise crucial experiments, each of which will, as nearly as possible, exclude one or more of the hypotheses. And I want to focus on that word exclude. Okay? That's important. And to get a better sense of why excluding, that is, so finding inconsistent evidence, actually gives you more information than consistent evidence. I'm going to introduce you to the Wasson selection task. You may have heard of this as the 4-card test. And we're going to do it twice. And I had a choice which way to do it first. Should I show you first the way that's very difficult, or first the way that it makes perfect sense, so that you can see that actually once you understand a system, this is pretty natural. And I went with, let's get it right the first time. So here we go. A man from out of state walks into a bar, having been told that only people over 21 will be drinking beer. So that's the hypothesis. To determine if that's true, he can ask questions, gather evidence, do experiments of the 4 people who are present. The question is, what is the fewest number of questions he can ask that will address the hypothesis? I'll give you a second to think about it. Pretty much, I think people are have experience with drinking ages and how the bartender or whoever has to determine whether someone can drink a beer. So we have a person drinking beer, a person drinking 7-Up, a person with gray hair and wrinkles, and a person with acne. So what's the fewest number? Well, the answer is 2. Okay? He needs to ask the beer drinker how old she is, and he needs to ask the person with acne what he's drinking. Okay? The idea being that acne indicates youth. All right, what about the other 2? Well, he could confirm that the person drinking 7-Up is under 21. It really doesn't matter how old she is because she isn't drinking beer. So asking her how old she is not going to help us learn anything about our hypothesis. Okay? He could also confirm that the person with gray hair and wrinkles is drinking beer, which might confirm that people over 21 drink beer, but it really doesn't matter because she's obviously over 21, so she can drink whatever she wants. Okay? It's the experiments that would have disproved the hypothesis that provided information. You card the beer drinker and you see what the young person is drinking. Because if the, if the person drinking beer is too young, that falsifies the hypothesis. If the person with acne who's too young is drinking beer, that falsifies the hypothesis. Okay, so that one's pretty straightforward. We pretty much recognize that situation and why you would do the experiments you would do. So here's one that's a little more abstract. And this is the one that's called, why it has the name, the 4-card test. These cards are cards that have letters on one side and numbers on the other. And the hypothesis you're testing is that if there's a vowel on one side, there's an even number on the other. So same question, what's the fewest number of cards you can turn over, experiments, to address this hypothesis? And I'll give you a minute. Say, go through it systematically again. Okay, if it doesn't jump out at you, ask yourself, what will I learn by turning over the U? What will I learn by turning over the J, the 4, the 13? Okay, now I've actually set this up to look exactly like the last one. Okay? And the answer is the same for the same reason. Okay? The answer is 2. We're going to go through it systematically now. If the U has an odd number on the other side, that is inconsistent and you're finished. You know the answer, the hypothesis is wrong. It doesn't matter what's on the other side of the consonant because our hypothesis is about vowels, doesn't matter. It doesn't really matter what's on the other side of the 4 because we're asking about vowels, not numbers. And the best that could happen is you have more of the same information that you've already got from turning over the U. So it's not useless. It would confirm the hypothesis, but it's really not going to give you anything more than turning over the U. So there's no point in turning it over. The 13 that has a consonant on the other side, that's irrelevant. But if there's a vowel on the other side, that is also inconsistent. That disproves the hypothesis. So just like carding the person who's drinking beer and finding out what the underage person is drinking were the experiments that could disprove your hypothesis. Okay? Again, it's the experiments that can show that you're wrong that actually give you the information you need. Okay? That's profound. That's a really important thing to remember. It's very human to say, oh, I believe such and such is true. I'm going to go look for evidence to support it. The scientific method is to look for evidence that would disprove what you believe. Okay? The point is, the experiments that give you the most information are the ones that have the potential to disprove your hypothesis. And that's what it means when it said that a hypothesis has to be falsifiable to be scientifically useful. Okay? And that goes back to Karl Popper. Insofar as a scientific statement speaks about reality, it must be falsifiable. And insofar as it is not falsifiable, it does not speak about reality. I would soften that to some extent. It's often very good to get confirmation. It helps to convince people of your idea when something is, when you can show over and over that it's true. Replication, for example, is an important kind of confirmation. What I would say is that a hypothesis that is falsifiable is what's going to give you ideas for the best experiments that are going to give you the most information. Okay. Now don't worry, because you might think, oh my God, trying to disprove my beloved hypothesis is going to make me feel extremely uncomfortable. Okay. But you have followed rule 1. You have alternative hypotheses, and therefore you have not fastened your affections unduly on any single one. So those two together, alternative hypotheses that you then try to knock down one by one through experiments. So that's Platt's first step and his second step: devise crucial experiments, each of which will, as nearly as possible, exclude one or more of the hypotheses. So when I get to part 2 of the series, I'm going to talk more about what you actually do when you're doing an experiment or designing an experiment. So moving from inside your head about how to be a scientist to at your bench or in your field. For the rest of my time today, I want to talk a little bit about controls. So controls are kind of in the middle of those two things. You have to think very carefully about controls, and then you have to do them. So what I want to think today about, or discuss today, the thinking part of it. What is it that's going on in your head, or what's a useful thing to have going on in your head when you are designing controls? So controls are not exactly alternative hypotheses, but they are attempts to disprove the validity not of your hypothesis, but of your techniques. And you do that to make sure you're not making any assumptions, because you want to believe not only that your hypothesis is right, but that your technique is both appropriate and working. Okay? So controls have a similar kind of role of challenging what you believe, but it's what you believe about your techniques, the way you're carrying on your experiment. This is actually part of a graphical outline for a workshop that I do on teaching practical science skills and tools. Don't go for the details. I simply want to point out that what we've been talking about so far, so that I can sort of explain how these two ideas fit together. So we've talked about the question, the multiple hypotheses, and the experiments that we think about doing using strong inference. Below here are some steps that you then take and the kinds of experiments that you can do. But I want to focus on the controls. So there are 3 controls that it's very important to always do, if at all possible. The positive control, the no treatment control, and the negative control. Now, these are not the only controls you have to do. Controls vary with techniques. Colleagues, advisors, the literature, those are good places to go to find out all the different controls you might have to do. But these 3 should always be done. Just make it a matter of habit. So anytime you plan an experiment, you should be planning 4 different experiments: the treatment itself, the no treatment control, the negative control, and the positive control. Okay, let's talk about these a little bit. So I want to, again, address the idea of what you're thinking about with controls rather than how you might actually do any particular control. So I want to talk about reasoning scientifically about your techniques. When you're observing or experimenting, and those are 2 different things, you are looking at a subset of individuals called your sample, and hoping to infer something about all of those things, the population. The problem is the technique you use could itself be causing whatever it is you're interested in. So if you're looking at the cause and effect, the cause might be the technique, not the drug you're testing or the intervention that you're trying. So for example, your hypothesis is that hearing the words, "he's so cute," makes quokkas smile. You're going to test this by having some people say, "he's so cute," to a sample of quokkas. So while I'm rebooting my PowerPoint, which just crashed, I want you to think about how might that technique of having people say, "he's so cute," to quokkas and seeing what they do, how could that technique on its own affect the result? And I'm going to restart my PowerPoint, so don't go away. Okay, so the whole story, where the controls fit in. Okay, any ideas? Okay. Well, you come up with an alternative hypothesis about the technique. So maybe quokkas smile when people are looking at them, and it has nothing to do with what we say about them. So how do you test that? How would you disprove that it's just that you're looking at them? Well, you check to see whether quokkas smile in the absence of people. Okay. The no treatment. You look at whether you see the effect, smiling, in the absence of your hypothesized cause, people. Okay. Okay. Another alternative hypothesis about the technique is maybe quokkas smile when people talk, and it has nothing to do with what is actually being said. So how do you test that? How would you disprove that it's just the fact of people talking? Well, you could check to see whether quokkas smile when someone says, "when is lunch?" instead of when they say, "he's so cute." Okay, those are the first two controls, the no treatment and what's called the negative control. The no treatment control tells you whether the effect is something that happens anyway, regardless of whether you try to cause it. So you can think of colds actually go way over time on their own. Okay, so pills might look useful, but in fact they're not. Okay? And I believe I've crashed again. So I'm just going to keep talking for a minute, and then I'm going to go ahead and close a little early and open up for questions. So no treatment, you think about in terms of disproving that it's your treatment itself that's having the effect. The negative control, which you do so that you have something with which you can compare a positive result. So you get what you predicted, you need to be able to compare that to the negative control, because you need to show that your technique is not what's causing the effect. You need to show that it's not being there with a camera and talking to quokkas that is making them smile. Okay? So you talk to them, you say something different, and you see whether they smile or not. Okay, I'm going to save the positive control for next time. It's a little peculiar because to talk about it, you have to use a lot of double negatives. So just as the negative control is important for you to compare with the positive result, the positive control you need in case you get a negative result. So if nothing happens, one of the alternative hypotheses about the technique is the technique just didn't work. Okay, maybe quokkas are deaf. Okay? Maybe when you talked to them, you stood too far away and they just couldn't hear you. So what you might do is you might make sure that if you say, "he's so cute," to something else, that something else can hear it. You want to check that your technique is actually working. And the reason you got a negative result is not because your technique didn't work. And I'm going to let the technology dictate that this is the end of this webinar. And I would be happy to take any questions if the technology exists.
Thank
Oh.
you. So,
Oh. Hey,
thanks, Danny.
there it is. Some of it anyway. Okay. Okay.
Well, thank you, Danny. That was a great presentation. I really enjoyed it.
Good.
So just to kind of give a short, brief recap. So we went over a little bit with heuristics. So, what our shortcuts are in thinking. And then you did some examples of how to disprove, of using experiments to disprove your hypotheses and making sure that you use the correct ones and what ones are irrelevant. And then you ended on the importance of controls, but finished right before the positive controls, which hopefully you'll be able to talk about next week.
Yes, for sure.
So now we will turn it over to our audience for questions. We have a few already, but if anybody else comes up with questions during our question session, please feel free to post it in the questions box that appears on the right-hand side of your screen. So our first question is from Jenna. And so she has a question about using designing experiments to disprove your hypothesis. So I think what she's trying to get at here is, how do you make sure that you're setting up an experiment that would disprove your hypothesis and not just kind of narrowly try to prove your hypothesis? Like, try to do yes, this should disprove our hypothesis, but it wouldn't entirely disprove it.
I'm gonna admit to being a very much a geek about this. Me, that's the fun part. I love the process of thinking through in advance what might or might not happen. And my silly joke about science always working perfectly, it doesn't. And a lot of the times, the reason science takes so long is because you thought about it in advance, you talked about it with your colleagues, you really did everything you could in advance, and it still doesn't work. And then you get to go and you get to troubleshoot, and you get to think, okay, I'm going to pull this apart. I'm going to think through again what happened, how I might address this little corner of it. The other reason the chemistry experiment is, in fact, a very bad model of how science actually works, is that it never works that way. You never get a result that absolutely disproves half of your hypotheses. It's much messier than that, but that's really the fun part. And how else can I do this? Maybe if I tweak this, maybe if I oh, geez, I didn't even realize that when I take the picture, there's a noise. Maybe they're responding to the noise of the camera. To me, that's the fun part. And so the advice is, think about it, talk about it, but then just jump in and do it, and let the data tell you, oh, okay, this didn't disprove anything. This is what went wrong. And then go back and think about it again. And talking with colleagues is the other thing. Just use your brain. Just think. It's a very creative process. I know a lot of people think that science is kind of, but it's not. And that's one of the places where the creativity comes into it, is the troubleshooting and the designing of ever better experiments.
That was always my favorite part, was the troubleshooting and figuring out, okay, how can you exactly figure this out?
Yeah.
So kind of, I guess, springboarding off of that, I have a question from Troy asking about, okay, so let's say you've designed an experiment, and I'm paraphrasing here. So let's say you've designed an experiment and you have your experiment that should disprove your hypothesis, but instead you get some sort of random result. And it's not you can tell that it's not, he says, you can tell it's not a technical error, it's an actual valid result. What do you do next?
Hopefully I'll get a chance to talk about that in the next webinar.
Oh, okay, so we're jumping ahead here.
That's fine. It happens. One of the things that's very difficult about biology is that there is a lot of randomness and there's a huge amount of variation. that's real. That's not because you used a bad measuring device or it was late and you counted wrong. There is genuine variation. And one of the other tools that we have for interpreting that sort of result is statistical reasoning. Mm-hmm. And again, statistics, whole careers go into figuring them out. I hope that I'll have time to give you a few rules of thumb. But if I can just distinguish between two different kinds of statistics. One is descriptive, one's inferential. And there are statistics that simply describe what you've got. Okay. Those are descriptive statistics. Those are things like mean, median, standard deviation. And then inferential statistics then allow you to compare what you've got to randomness. So you compare to if there wasn't anything special going on. And that statistic can give you a very good guidepost. So if what you got is the same as random, that's the same as saying my hypothesis was incorrect. So in fact, randomness in particular is a result that does disprove any hypothesis that said, this isn't random, this is because of this drug, or that's because I took the starfish away. Or so that may be the answer, and that's the answer. If those are the data, those are the data. And you get to go back to the drawing board and say, well, wait a minute, what else could it be? It wasn't this, because that apparently didn't matter. Okay? So what else might it be? And again, you get to go back and rethink it. But don't think of statistics as this horrible, oh my God. Think of statistics as a really useful tool that can specifically tell you whether or not what you saw is random. Does that help? I don't know if that's helpful.
Yeah, I think that's helpful. And then we have a question from Lindsay. This is a little bit more philosophical. And so she asks, what do you have any advice for when your advisor tells you that you need to get X result for this experiment? Or something a little bit more narrow, I guess, maybe a little bit more broadly, like you need to, like, we know that all this work, like we know the model, and we just have to do this experiment to confirm the model, and you may not get that result. Like, how might you deal with that? Or do you have any advice for younger researchers with that?
Advice for younger researchers is to take your result and in a very excited way, go running into your advisor's office. Oh my God, this is so great. We were wrong. And you can present it that way. On a different level, it's, again, I tried very hard to, and I hope I got across that these are my opinions. These, I believe, are useful tools, useful intellectual tools, useful ways of thinking about asking questions, how to get the most reliable answers. There are other ways to do it. And I know, for example, that I'm just going to go back to statistics for a second. The rule or the law as set down by the international group that decides these things is that the correct way to report a measurement is the mean and the standard deviation. Mm-hmm. There are entire fields of study where it is considered perfectly acceptable to report the mean and the standard error. Now, that's not right. The rule is standard deviation, and the reason for that is because standard deviation is standard. It does allow you to compare data sets. Standard error doesn't do that, and yet that's the convention. So it's possible that your advisor is showing you how it is done, how it's always been done. Whether as a graduate student is the right time to challenge that or not, kind of depends on your advisor. But I really think that assuming that the advisor is not just trying to prove her pet idea,
Mm-hmm.
Just treating it as, isn't this great? It didn't work out. I got the opposite result. Can you help me figure out what this means? I think is probably a useful way to approach the situation.
Yeah, I think that make it into kind of an exciting thing as opposed to a, oh no, this is a catastrophe.
Right.
This is an opportunity.
It's an opportunity, and part of the thinking that it's a catastrophe is the assumption that your advisor is not smart enough to judge their own ideas or to see where something's gone wrong. And that's usually unfounded. Someone's gotten as far as being your advisor. They're probably pretty smart and are open to being corrected. And the data are the data. You can't, that's the bottom line.
Yeah, that was my postdoc advisor's favorite saying, the data are what the data are.
Yeah, exactly.
And then we have a question from Fanibo. And so they ask, is it compulsory to have a hypothesis for every experiment? Like, what if there are no pointers? And I'm guessing that this might be in the case of what happens if you do this sort of experiment, like maybe doing microarrays and seeing what genes go up and down if you apply some stimulus.
Great question, especially because now all the granting agencies say they want hypothesis-driven projects. First, I want to distinguish and talk for a minute. I didn't talk about this before, but the difference between an observation and an experiment. So, and I consider things like microarrays observations. What's there? Okay. An experiment is specifically something where you introduce a new variable. You manipulate something and see what happens. If all you're doing, it's not all you're doing. If what you're doing is the description, the original observations, then no, probably having a hypothesis is going to work against you for the reasons we've been talking about, that you want to believe something's true. So if it's an observation, no, you do not want a hypothesis. If it's an experiment, it's certainly possible, and I would probably, if you wanted to put vocabulary on it, I would say that first one where you just say, oh God, what happens if I mix blue jay liver in with this, which is a real experiment, by the way. What happens? Sure, that's fine. And if you keep going that way, it's going to be very hard to stay on a road towards something that's publishable. Unfortunately, we are long past the time where you could just simply follow your curiosity. At some point, you are going to want to take the evidence you have and pull it all together and say, what's the best explanation for this? Can I come up with explanations and then test them to see which one fits the best? So yeah, if it's an observation, don't come up with a hypothesis. And not having a hypothesis is a fine way to start, but to keep going towards the end of something in this day and age, yeah, you kind of do need a theory within that you're working within.
Yeah, I think that's a really good point about not having a hypothesis when you're doing some sort of observational type experiment, because I know when I was in grad school, the postdoc in my lab ended up getting an entire line of research that she now has as a tenure track professor by just doing let's see what happens here. And then she got a really strange result, and it was valid, and it turns out that it's elucidated an entirely new mechanism.
That's fantastic. There's one of my favorite stories is the guys who were playing with Scotch tape in their pencils.
Oh, and they heard that one.
Put Scotch tape on the pencil and they pulled it off and discovered graphene. They got a single layer and studied it, and that turned into a Nobel Prize. So by all means, indulge your curiosity without constraint when you're making observations.
I like that. Well, I think that's a good place to end.
So that brings us to the end of today's webinar. Thanks, Danny and Amanda, for an inspiring presentation and a great discussion. And thanks to you, the audience, for taking the time to attend and listen in. Keep an eye out for part 2 of this webinar series, also being presented by Danny, titled Confirmation Bias and the Scientific Method 2, Applying the Scientific Method. So until next time, good luck in your research and goodbye from all of us at Bite Size Bio.